Yeah. Okay. So, good evening, everyone, to the week 9 of problem solving sessions of computational complexity. My name is Bhavya. I'm a PhD scholar from IIT Madras, and this time I'll just get a bit into the recap of what is done and maybe try to explain the theory once again. And also, I would like to solve a question that was there in the assignment. Last time there was a bit of a confusion, so I want to tackle that. Okay. So, yeah, maybe I'll do that first. Maybe I'll try to solve this question. Okay. So, the question is, what is the value of I for which we know that log space uniform NCI is contained in L, is contained in NL, is contained in log space uniform NCI plus 1. Okay, that is the question. So, do you have any guesses, or maybe you know the answer already, Suraj? Yeah, am I audible? Oh, okay. Yeah, okay, 1. Yeah, that's right. Okay, now question is, why is it 1? So, answer is 1. Okay, now why should the answer be 1? So, that is NC1 is contained in NL, is contained in L, is contained in NL, is contained in NC2. And these are both log space uniform. And this is also log space uniform. Okay. Now, what is NC1? Okay. This is a um, class of functions or languages. Okay. Fn computed by circuit families Cn n is at least 0. Okay. And computed by and family, the circuit family is polynomial sized. That is a property of NC. And another property is that it is bounded Fanon. Okay, bounded Fanon. What does that mean? That means every gate in the circuit, maybe an OR gate and or AND gate, whatever, is bound. The number of inputs to a gate is bounded by a constant. So it may be 2 or 3 or 4, whatever, but it needs to be constant every gate. And without loss of generality, we assume it's 2, because with a constant that blow up, we can simulate any bounded Fanon circuit with Fanon 2, so as a Fanon 2 circuit. Okay, and okay, polynomial sized bounded Fanon, and next we have um, since it's NC1, what does the 1 stand here for? That is the depth of the circuit, which is log n, order log n depth. If it was NC2, it means log square n depth. If it was NC3, it means log cube n depth, and so on. Okay, and this is what NC1 is. What we want to say is NC1 is uniform log space uniform NC1. For now, let's not care about log space uniform. Okay, NC1 is contained in L. That is what we want to say. Okay, L. Okay, so what is the model for the L? The model for L is the characterization of L is a log space, deterministic log space Turing machine. And here NC1 is again this particular circuit family. Now, I had given a long explanation in one of the previous sessions about uniformity, right? So here we have NC1 as a non-uniform class, which means for every different input, I need a different circuit. Different input length, I need a different circuit. While a Turing machine is uniform, right? That is, for every different input length, the same Turing machine will still work. It will still compute the language. Okay. Now that you have that, you are, and how does it work? When do you say you have one complexity class C1 and you want to show that it is contained in C2? But usually, what you do is you take the Turing machine, okay, any Turing machine in C1, and you show that any Turing machine in C1 can be simulated by any Turing machine in C2. For example, if this was L, if you wanted to show L, and this is NL or P or whatever, you wanted to show this, then you say that, okay, any non-deterministic log space Turing machine can simulate an arbitrary log space, deterministic log space Turing machine, and so on. You do that. But this is fine because you're only talking about Turing machines simulating other Turing machines, right? Problem arises when you have uniformity in mind, okay? Non-uniformity. For example, this is a non-uniform class, and this is uniform. Now, okay, you might ask like, okay, so one is non-uniform, the other is uniform. What is the problem? Well, thing is, now what you want to do is you want to say that, okay, any language that is computed by an NC1 circuit can also be computed by a log space Turing machine. That is what you want to say. But now you want to say, okay, now taking the same idea, you want to say about simulating Turing machines. You want to say that, any Turing machine can simulate a log space, NC1 circuit. That is what you want to say. You want to say any L machine can simulate NC1 circuit. Any NC1 circuit. That is what you want to say. Okay, well and good, but NC1 circuit computing what? The circuit family computing a language, because we are already using one L here, let's say computing A, okay, computing this language. But what is the problem that arises? Okay, so you have your L machine, okay, L machine, let me call it Turing machine M, okay, and there is an input X. So what does it do? Turing machine during its run simulate or whatever, evaluate, let's say evaluate C on X. This is what Turing machine M does. But what is the problem here? What is the problem here is that, okay, first of all, how do I get C? Well, you may say, okay, C could be hard coded into the Turing machine. Like, for example, doing this. Turing machine simulating other Turing machines, you can just hard code it into the input. But here is where the problem arises. Since there is no single circuit, okay, for the entire language, I need to hard code every possible circuit for every possible length in the circuit family, which is not possible for us, right? It may not be possible always. So that is when, advice comes to picture, either advice or you include uniformity. So either say that, okay, before evaluating C on X, okay, what do I do? here compute description of C on the length of x many bits. Okay, if this is possible, computing the description of C, okay, which takes in this the n many bits, where n is the length of x, then what I can do is I can evaluate C on x. But this should be possible. Is it always possible? No, it is not always possible. Otherwise, we could even solve, entire p slash poly in say p, which should mean that even undecidable language you can solve. But this is not always possible. But we'll only restrict to the cases where it is possible. Okay, let us say that the circuit that we are able to evaluate, the description also we can compute in logarithmic space. Okay, the description also we can compute in logarithmic space. Then that language is what is called a log space uniform. That set of circuit is what is called a log space uniform set of circuits, which you can compute in log space. And so you get rid of this non-uniformity problem, and okay, and therefore our claim changes. Okay, need to show any L machine can simulate log space uniform NC1 circuit family computing an A contained sigma star. Any A contained sigma star. Okay, so good. Now we have that picture. Now let's work it out. Okay, NC is contained in NL. How do you do that? Well, I want to show that first of all, that means that if X is in A, if and only if that particular circuit family on X will give a 1. So, given input X, okay, so, okay, given input X, I want to evaluate CX on X. Okay, so here is the idea. Okay, and I have a deterministic log space Turing machine M, and what is the input? Input is some X. First step, what I do is find circuit CX. Okay, I look at the length of X and compute the description of the circuit. Okay, and the next what I do is I run CX on X if CX equals on X equals 1, then output yes, otherwise output no. This is the logic. Now step 1, is possible. Why is it possible? Because why is step 1 possible? Because this C of, or this circuit family is log space uniform. Okay, because it's log space uniform, I can compute the description of CF, CX. Okay. Now next thing is step 2, possible. This is my claim. Okay. So this is the claim that step 2 is possible. Okay. So how do you? Okay. So that is evaluation of a poly-sized unbounded Fanon, not unbounded, sorry. Oh, did I write unbounded before? Bounded, that's correct. Bounded Fanon, okay. And the next thing is log depth circuits is possible in log space. Okay, so this is the claim. So how do you do that? Now let's say you have a circuit. Okay, the circuit looks something like this. Let's say, of course, it may not be very triangular in shape, but we know that there is X as the input and there is a single output. Okay. Now, what additional information do we know? Well, the the depth of the circuit is order log n. Okay. Now, if I have an AND, I could have several gates here. Let's say the top gate is an AND gate. It has 2 inputs. And next one is an OR gate, 2 inputs. And here another AND gate, let's say. And it may so happen that, this gate is connected to this gate. Because this is a circuit, remember, not a formula. Okay. This is an AND gate. And this is how it goes. This is what a circuit looks like, which is of log n, and then the size is polynomial. Okay, log n depth and size is polynomial. Now the important thing to note is that it is of depth log n. Okay. Now what you do is you recursively go down the circuit. Okay, and try to evaluate it. Well, how do you evaluate it? Okay, so what you do is, okay, any gate, okay, can be identified by a path from the root. Okay, and what you do is, okay, and how do you do it? Let's say I want to identify, suppose say this gate. Okay, and I call it gate, I call it G. How do I identify it? Well, here is the path that identifies it from the root. Okay, G can be identified as from the root, go left, and then go again left, and then go right. This is how you can identify it, right? Go left, and then go right. Right? This is how a gate can be identified. Now, I can do this for every gate possible, but of course I don't have that much space to remember this for every gate, right? And this circuit is given like a read-only thing to us. Okay, I cannot do any modifications to the circuit and so on. And but this is how I can uniquely identify a gate, right? So what do I do is I do a DFS. I do a DFS. And what do I do during the DFS? I use this path of going to left, going to right, and so on. And when I reach the deepest gate, I will make an evaluation of that gate. Okay, I'll make an evaluation of that gate, do a DFS. Okay, and on reaching the deepest unknown gate, unevaluated gate, whatever. Okay, evaluate it. But how do I evaluate it again? What I'll do is I'll evaluate it recursively. Correct? So I do the same trick again. I do a DFS once again. Okay. So the idea is that, okay, I want to know what this AND evaluates to. Okay. I want to know what this AND evaluates to. So what I do, I explore this path. I explore an arbitrary path. Okay. I choose the left one first. And then I choose the left. Then I choose the right. And then I get a gate. And I don't know the value. Okay. And below this, let's say I know the value. Okay. And deepest unknown gate. Well, but of course, but when I reach this gate, okay, and let's say there are a series of other gates below there, I recursively evaluate this. How do I do that? Okay, I again go down some path. And then for each of those gates, again, I go down some path. Okay. And then what happens is, as I reach the bottommost layer, okay, and there leaves I know, for that particular path, there will be a leaf, okay, for some path, okay, for some path, I'll end up with a leaf, okay, and this leaf will set the gate to OR and whatever, okay, let's say there is an OR, then this will give a 1, and if this was an AND, then I needed to look at both the leaves. And so on. I do this, and okay, this gives a 1. I know that. Now, what the idea is that, okay, but I know only about that single path, right? And then there may be another gate out here. What I do is, to do that, I do the entire computation once again. Starting from here, I just evaluate once again. Okay, this is a classic log space evaluation kind of idea. For example, Savages also did something similar. Okay, to get a single index, you do the evaluation once again. Of course, the polynomial, the time taken is still polynomial, of course, but it may take a huge polynomial time. Okay, which may not be practically feasible, but as long as it is polynomial, we don't care. Okay, and so every time you need a gate, to get the value of a gate, I do this entire business once again. Okay, so that is what I mean by doing it recursively. But what we notice is every time I just need to remember this path of left, right, and so on, right? Which can be remembered by zeros and ones, 0, 0, 1, and so on. And what is the maximum length of a path? Since this is equal to the depth of circuit, this is equal to order log n, because it is an NC1 circuit. Okay, and yeah.
Sir, why we are only considering one path from the gate, as gate output also depend on all its inputs?
Yeah. Now, why are we considering only one path? We are not actually considering one path. What we are actually doing is we are not going only on a single path. Okay, what we are trying to do is we are trying to fix the input at each gate. Okay, as we go up. Now, how do you want to do that? Okay, and we are not actually only looking at one path. Okay, we are actually doing a DFS, and we are doing across all paths. So, okay, it's showing some technical error. Are you able to listen to me?
Yes,
Yeah.
yes.
Okay. Okay. Good. So, okay, it's good that you asked me. So here is an AND gate at the top. Okay. I want to know what this AND gate evaluates to finally. Now, what is this AND gate equal to? This AND gate is equal to the output is equal to the AND of these two gates, and these two gates. Okay, and this gate is again dependent on the inputs of these two gates at the bottom, and so on and so forth. Okay. Now, what we do is I want to know the output here. I will recursively check what is the output here. And I'll recursively check what is the output here. Okay, so I'll write the algorithm. Okay, I'll write the algorithm. Um, I'll write the algorithm. Okay, um, take root gate. Okay, I'll call that algorithm uh, eval nc1. Okay, and what do I do is eval nc1, and I'll uh, call it gate g. Okay, some gate g, and take g. Okay, take gate g, and so suppose g takes as input gates g1 and g2. So this is what it looks like. Okay, g is a gate which takes input from g1 and g2. Okay, now what do I say? Um, um, I do left is equal to, okay, eval nc1 gate g1, and right is equal to eval nc1 gate g2. Now, if g is AND gate, then return left and right. G is OR gate, then else if G is OR gate, then return left or right. This is fine. Is it fine?
Yes.
You understand the recursion. Okay, good. Now you are doing this. Okay, what you are doing this is you are recursively so at least from face value you should be convinced that if I give the root here, okay, if I give the root, then it should be able to do this. Okay, the formal proof would be something by using induction, but now bear with me. Okay, what you are now doing is, okay, what you are now doing is, now how does this eval nc work? How does this eval nc1 work? Okay, there should be some kind of evaluation happening in between also, because the problem, what is the problem about doing this straight in the straightforward way is, now what is the problem is that I need to remember too much information. Okay, how much information do I need to remember during the recursion? Well, g1 itself will return some values, g2 itself will return some values, and so on, and I'll need polynomial number of bits to remember the information for each gate. But the idea is to actually make because but I hope you get it. What I'm saying is that um G1 itself will depend on several gates. G2 itself will depend on several gates, and each of their out. So this the memory is sort of branching. Okay, I need to account for more and more nodes out here, more and more gates, and which is a problem for us because now since the circuit is of polynomial depth, I'm remembering logarithmic depth. I'm remembering polynomial amount of information. finite amount of bits. So I cannot do this directly. Okay, what I want to do is I want to make this algorithm sequential at the loss of time. That is fine. Okay, at the loss of time, which is fine for us. But what I want is I want lesser space used for the same algorithm. Okay, modifying this algorithm. So, but I hope that you are understanding that we are doing some kind of BFS or DFS here, right? We are doing sort of a BFS. That is what I believe for this particular algorithm. So now what I want to do is I want to this kind of recursive dependency. I want to remove it by the following way. I will explore this branch first. Okay, I'll keep going, left, 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 and so on. Okay, and there are of course unknown nodes here. Okay, but what do I do? Okay, what do I do? I want to find the output of a certain gate. Okay, let's say I go down this path and I want to find the output of a certain gate. I go down this path, I want to find the output of a certain gate. And what do I do is, let's say I want to find the output of this gate. Then I'll do the left-right business once again. Okay, so this is all recursively happening. Okay, I'll do the left-right business once again, and then come to the conclusion and then do that and then do the left-right business once again for each of the following gates and so on, and then fix the value of this. So I'm not looking, like you said, I'm not actually only talking about one path. Okay, and when this DFS occurs, I'll look at the other path also. But the idea is that if I want to find the value of any gate, I'll recompute the entire process using this left-right business. Okay, if I want to find the value of G2, then I'll use the left-right business recursively, which means doing left-right business on G2 means that I need to recursively find, do the left-right business on this guy also, and so on and so forth. But when I do this, I don't need to, which is an important thing that I did not say. Okay, that if I do a certain left-right business here, okay, I will not take any more additional space than what is required. Okay, so if this is the circuit and this is the depth D and this is my storage D here. Okay, and I go down a path. Okay, and then I do left, left, right, and so on, left, left, right, and so on. And here I want to find the value of G, right? So I do the left, right business, and I can use this remaining space to do left, right, left, and here I do left, right, left. Okay, and then I finally reach a leaf, and the leaf is 1, and then I go up. Okay, and then I go up here. I know this guy is 1, and then I go down once again. I reach, let's say, another leaf. It's a 0, and let's say this is an OR gate. Then I go back, and this is 1. So what I'm doing is, okay, let me illustrate that once again. Okay. I go left, right, and left once again. I reach a leaf, which is 1. Okay, this value is 2. 1. I remember it. Okay, in some other place. Okay, it's a constant only, so I don't care. Okay, and then I go one step up, and then I go right here once again because I'm doing a DFS. So I go a right here. Okay, and let's say this was not a leaf. No problem. I'll go deeper. I'll do left, right, left business once again. But let's and I'll add things to it. Left, right, whatever. But let's say it was a leaf. Okay. Let's say it was a leaf, and that is an input. And let's say it was a 0. The input was a 0. And let's say this gate on top was an OR. So what do we have now? Okay, I have enough information. One is 1, the other is 0. OR of them is a 1. So I remove this guy, and I know at this position the output is a 1. That's right, Suraj, right?
Yes, sir.
Now what do? I backtrack once again. I go up. Okay. I know this guy is a 1. Okay. I know this OR gate evaluates to a 1 now. I'll forget this information because it's no more required to me. I'll remember for this new gate. Okay. For this gate, call it G1. Okay. This OR gate G1. I know that G1 is 1. I now backtrack. Get here. I remove the information. Okay. And okay, so I need to do an additional. Okay, so since I backtracked, I'll remove this information. Now I need to go left. I need to go left because I had moved a right. Then I'll add a L here. Then what do? I have a gate here. Now I have again two choices. I can move left or right. Let's say I move left again. Then I'll add a left here, and so on and so forth until I reach a leaf, and I keep doing this. Okay, and then I obtain the information that, oh, okay, so this guy is a also a 1. Okay, and let's say the gate was an AND. Okay, let's say the gate here, which is suppose say G2, is an and both the inputs are 1, so then G2 will evaluate to a 1, and I remove both this information. And so you see, right, that given just this depth d amount of space, I can evaluate for any gate using this DFS idea. And I start this process from the root, and we are now, I think you can see that we are actually going through all paths because we are essentially following a DFS algorithm. And once the value of root is inductively fixed by this process, we'll get the desired output. That is the evaluation of the circuit. So is that fine, Suraj?
Yes, sir.
Okay.
Means, sir, we are recomputing and again to save the space.
Right. So yeah. So this is a very important idea in space complexity, that uh, the idea that you can recompute. I mean, it's not like you can recompute. It's more like we are forced to recompute each time. But I agree that this will take a lot of time. Okay, this will take a lot of time because I mean you are going across so many paths. Okay, and the polynomial time, it'll still take polynomial time. It'll take a huge amount of polynomial time probably, but we are fine with it as long as it is not taking more than log space. Okay, so yeah. So now that you do this, it is possible to evaluate. So it is possible to evaluate an NC1 circuit in log space. So you see that this D is log n for us. If it was not log space, then this would not be possible in log space. So you can even generalize this idea to say that NC K uniform NCK, of course, log to the K uniform, is contained in D space log K. Right, Suraj?
Yes,
Yeah.
sir. Yes, sir.
Yeah, same idea. Okay. If the depth is d, you will take d space. If the depth is log to the kn, because nc, what does nck mean? Log to the kn depth. Okay, is contained in d space log to the kn. So what does that mean? That means nc2 is contained in d space log square n, right? Right.
Yes, sir.
Now, do you know an algorithm? Do you know a theorem which says something interesting about log square n space? I think that was a bit vague question. um, can reachability be done in log square n space? So what is reachability is complete for a complexity class, right? So what complexity class would that be? Reachability is NL complete, right?
Yes, sir.
And reachability, we know that reachability can be done in log square n space. And what theorem is that? It is Savage's theorem. Says NL is contained in D space log square n. This is Savage's theorem. Okay, 1978. Now you have NC2 is contained in D space log square n, and NL is also contained in D space log square n. So, question is, what is the connection between these two, NC2 and NL? Right. So this is the question, and this is what this assignment question is asking. That actually NC2 contains NL. So now you can say that NC2 contains NL. So NC2 contains NL. So that is what this question is all about. So that we are left to prove the next part. Of course, we know this trivially. Now we want to show that NL is contained in NC2. I here, we chose I to be 1, right? So I plus 1 is 2. So our part 2 is NC2, okay, NL is contained in NC2. So this is the next question. And okay, so how do you do this? Not just NC2, it's log space uniform NC2. Okay, actually log square space uniform will also will work. Huh. One moment. Yeah, yeah, okay. Okay, so how do you do this? Okay, so um, you'll show that reachability, okay, which is NL complete by the way, can be solved by NC2 circuits. Now again, to remember what is NC2, firstly it's polynomial sized with respect to input length and bounded fan in, and finally um, log square depth. Okay, so we saw it in both the directions now. First, increasing the depth by a log factor, we can reach NL. From L all the way we can reach to NL. And another was Savage's theorem. Increasing the space by a log factor, okay, we can get till NL. So these are two ways of saying the same thing. Okay. Now, okay, so reaches NL complete. As long as we can solve a NL complete language using NC2 circuit, entirety of NL can be solved by log space uniform NC2. So here I want to revisit a question that we did before. Okay, that was about matrix multiplication. Okay, so what was the idea is that so what is what is um, let's say C is equal to A times B. Okay, and A and B are matrices um, let's say n cross n matrices. Okay, and yeah, so and what is the formula for matrix multiplication? Well, what you do is you take a row and take a column and you multiply each element from this row to this each element in this column. Okay, and you do that for every row. Okay, now let's say I fix a row I and I fix a column J. Okay, and I want to find the entry here. I want to find this entry. Okay, then what do? I take the ith row, I take the same row, ith row, and every what do? I multiply it with every element in J, not every element, sorry, the corresponding element in J, and then I add them, right? So what is the formula? I add, okay, I add every element, okay, I add uh, multiplication of AI and so this is K goes from 1 to N, so this is K, okay, whichever place I am currently looking at. Okay, K will be multiplied with K here. Okay, AIK times B. Now this time kth row, jth column. So this is the formula for matrix, compact representation of formula for matrix multiplication, right? Now we already saw that matrix multiplication. Suppose, okay, A is the adjacency matrix of a graph G, a directed graph G. Okay, then what does A mean? A means uh, um, um, A U V position equals 1 means there exists a path of length 1 from U to V. Or in other words, if at UV position it is 1, then it simply means that there is an edge from U to V or a path of length 1. Same thing. And we also saw that when you square this and UV equals 1, then there exists a path of length 2 from U to V. And you keep doing this, and you, let's say, do it until M UV equals 1. If you square it M times, power it M times, then again there exists a path of length M from U to V. So I think you remember that. Suraj, do you remember this?
Yes, sir. Yes,
Yeah.
remember.
So I don't need to get back into this. Good. So yeah. So we know this information. Now, what does that mean? That can we do reachability here? So since we are talking about paths, this sounds like reachability only. No. Well, what does reachability say? Reachability says given an S and T, I need to check whether there is a path from S to T. Here it's slightly different. Here the length is mentioned. So this is a variant of reachability. What is reachm? Reachm is GSTM, okay, such that there exists a path from S to T, okay, there exists a path from S to T of length M. But this is not exactly reachability. What is reach? Reach is like the union of all this. There may be a path of length 1, there may be a path of length 2, and it is still fine. And there may be a path of length n minus 1 to be exact. So now question is like, um, we are trying to solve a harder problem. Okay, first of all, I've not even NC2 means only or and and. No, here we are doing multiplication and addition. So I've not even entered that place yet. Right now, um, uh, um, okay, yeah, that is another thing. Okay, and this is path of length exactly 2, exactly, not at most. If it was at most, then it's fine, right? Because why? Because I can even say reach as the following. Okay, another formulation of reach is GSTM. There exists a path from S to T of length at most M. And this is again reachable. Oh no, not M. I'll remove M here. At most N or N minus 1, whatever. N, where N is the number of it is. This is reachability, right? Changing from exact reach, this reach M, okay, to at most N minus, to at most N minus 1, I have again obtained reachability. So this is a key idea here. Why? Because I'll now demonstrate an example. It'll all be clear soon. Okay. So let's say I have this graph. 1 goes to 2, 2 goes to 3, 3 goes to 4. Okay. And what does the matrix look like? Okay. Um, um, Adjacency matrix looks like 0, 0. But yeah, okay. And here 2 0 0 0 0. I'm multiplying. Okay, I'm doing a square. Okay, and this is arithmetic multiplication. Okay, like the classic matrix multiplication. 1 goes to 2, and 2 goes to 3, and 3 goes to 4. Hmm. This is correct. Now let us multiply them. Okay, so first row, first column is 0. Okay, okay, I'll just quickly fill this. One goes. So let's try the first row and second column. Oh, first row and second column gives a 1, right? And rest gives 0. Oh no, but oh, this does not give a 1. First row and third column gives a 1. Now second row and first column, let's multiply. Second row and first column will be a 0. Second row, second column will also be a 0. Second row, third column will also be a 0. Second row, fourth column will now be a 1. And now if you try multiplying, the rest will all be 0. Now, so this is to reach from U to V in 2 steps. Right. This is the problem here, that we have forgotten on the way. We have forgotten that, this 1 could reach 2. We are getting 0 here, but previously it was a 1. We've also forgotten that 2 could reach 3 in one step. And we've also forgotten that 3 can reach 4 in one step. We've forgotten this information. So I keep doing this. So if we could somehow remember this information, if we could somehow remember that the fact that it was still reachable earlier, okay, we could actually do just simply a to the power n and then check from s to t whether there is a 1 or not. That is, whether there is a path of any length or not. Because the fact that we remember it, okay, if these zeros I turn it into ones, okay, this means that it was reachable by a path of length at most 2, right? That is exactly what we are trying to emulate now. Okay. Earlier paths forgotten. Earlier, not path exactly, reachability information. Reachability info is forgotten. Okay. And what is the solution to that? Instead of arithmetic matrix multiplication, we do Boolean matrix multiplication. Okay. And what is Boolean matrix multiplication? Here is your arithmetic matrix multiplication, right? This is your arithmetic matrix multiplication. I'll change addition to OR and multiplication to AND. And because of this property of AND and ORs, you will soon see that we are actually able to remember information. Okay. So let's do the same thing. Okay. And this time I'll also do a slight modification. Since every vertex is reachable to itself, from a reachability sense, they are reachable to themselves, right? So I'll set the diagonal elements to 1. Okay. Now we'll multiply it, but this time we'll do Boolean matrix multiplication. Okay. So here um, um, okay, let's do Boolean matrix multiplication. What is this? Yeah. So this row and this row, this guy will this guy will do 1 and 1 and 1 and 0, 0 and 0, 0 and 0 and so on. 1 and 1 will give 1, and OR across all of them will give a 1. Similarly, I'll do this and this, right, which will be 1 again. And then I'll do the first row, third column, which will be 1 again. First row, fourth column, which will be 0. Now I'll do second row, first column, okay, which will be 0. Second row, second column, which will be 1. Second row, third column, which will be 1. Second row, fourth column will also be 1. Third row, first column will be 0. Third row, second column will also be a 0. Third row, third column will be a 1. And third or fourth column will be a 1. And finally, this will be a 0, this will be a 0, this will be a 0, and this will be a 1. Now this is what we have here. Okay, this is a square in the Boolean sense, Boolean multiplication. Okay, now let's see what it causes. Okay, so I add these vertices 1, 2, 3, and 4. Right, one can obviously reach 1, but one can now reach 2 also, and one can now reach 3 also. This is what it shows. 2 can reach 2, 3, 4. 2 can reach 4 also. And 3 can reach itself as well as 4. And 4 can reach itself. Now look at the original graph and what we've obtained now. Now we are also preserving the fact that we can move in 2 steps to a certain vertex, as well as preserving that we could move to a particular vertex with just 1 step also. So you can see that the information is remembered, right? Suraj, can you see that?
Yes, sir.
Yeah. So this, now the information is preserved. So now the idea is compute a to the n, or a to the n minus 1. Okay. And check entry a to the n s t. If it is 1, then but we are talking about circuit simulating. So then output entry this. Now remember, we want an NC2 circuit to do this. But let's just see an arbitrary. Let's see the most trivial circuit that does this. Okay. So let's say we are trying to do a square. Okay, a square would be something like I have the adjacency matrix A here. Okay, and then first I do AND across two pairs. Okay, AND across AIK, BKJ, and so on. So I do and 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 there may be some AND that is sharing and so on, AND gates, and then I do an OR. So A square is computed by this. Okay. Now, how? Okay, so you have this. Now, how do you do A cube? A cube would be, again, you have your input, which is the adjacency matrix A of the graph. Okay. And then what you do is you compute A square. Okay. And even A square has several computations. And now what you do is you take these two and A square will give you a single position. Okay, something like A square ij, and here you'll compute OR of this and then compute to a bigger AND. Okay, and then another OR which takes in another A square, and this guy also takes things from here and takes one input from the original this. So we are doing the recomputation of the entire thing. Okay, this is only for A cube, and you do this across, and you see the problem here, right? First of all, the size is very big. Okay, and that is another problem. And another problem, okay, is that to compute. Okay, I'll just show for this A square. What is the problem here? Is this an NC1 circuit? Suraj, can you tell me, is this NC1 or not?
Yes, sir.
Why is it NC1?
Uh, so because it is of only depth 2.
It is of depth 2, right? And what is the other condition of NC1?
Uh, Polynomial number of
That is
initial
also true.
gates.
That is also true, right? And final condition is,
Bounded fanning.
yeah. So is it bounded Fanon? Or
Yes, sir.
gate, this OR gate, how many inputs does it have? It takes 1, 2, 3, 4, 5, 6, n inputs, right? So is it bounded Fanon?
Yes, sir.
Oh, no. It is not bounded Fanon. N is the input. With the input, the gates number of inputs will change with the input to the circuit, input length to the circuit. If it is something like 2, 3, some constant, then it is bounded Fanon. If it is n, it is not bounded Fanon. Is that clear?
Yes, sir.
Okay, so this is not bounded. Even if it was something like log n or something very small, okay, root n, whatever, it is not bounded Fanon. So now that we know, okay, this is not bounded Fanon and this is not NC1. unbounded fan in. Now what do you need to do? You need to convert it into a bounded fan in circuit, right? So on converting, what is the problem that happens when you convert it to a bounded fan in? The depth will increase. The depth will increase by a log factor, which will be log n. If it is, I think we did this exercise before. If the fan in is k, I can change it into fan in 2 by a log n factor. Okay, so now just, yeah, just one moment. Yeah, so this, okay, so log n, but this is good. Okay, log n is good. A square we can do it in nc1. Now this is nc1. This is purely nc1. We can see, right? But as soon as we do a cube, the depth has increased, right? Okay, I can make this into bounded fan-in, no problem, by log n factor, but this has still increased. Now if I do 8, this has increased by so the depth has become 2. So which means since this will take log n depth, this guy on converting it into bounded, I will take log n depth, and this guy will take log n depth. So this means 2 log n, and then I do a cube, a to the 4. Then I'll add one more level into it, and it will be 3 log n, and a to the 5 will add one more layer to it. It will be 4 log n depth. What do I want? I want e to the n, which will be n log n depth, or n minus 1 log n depth. Which is not nc1. So do you have any suggestion how we can compute a to the n more efficiently?
Sir, maybe we can forget the down labels after computing.
Yeah. But if you were evaluating a circuit using a Turing machine, there is a concept of memory, but we are doing purely circuits. Okay, there is no Turing machine here. The problem is reachability, and we are building circuits, and there is no concept of memory or forgetting and so on. But I'll give you a hint that you don't need to even do some circuit theoretic trick. Okay, it's a algorithm trick. It is a standard trick in design and analysis of algorithms. Okay, anything to do with powering. How can you compute powers more efficiently?
Maybe like to compute the a to power 4, we can do a square into a square.
Right. Good. Nice. Good. Very good. Yes. And nice. Good. And the technical term for it is what is called repeated powering or repeated squaring. Okay. And this is a in analysis algorithms it's a DP technique, right? It is a very simple example of a DP, dynamic programming algorithm. Okay, and exactly, to compute a to the 4, it is as good as saying a square into a square. And okay, so to compute a to the 4, it is as good as saying a square times a square. And to compute, say, a to the 8, okay, I want to do that. Then what can I do? I can do a square into a square and times a square into a square, which is nothing but squaring this again. Okay, and this is, what is this? This is a square square. And what is this? Um, a square square square, and so on. A to the n would be a square square square, and so on. You keep doing this square. And how many times do you need to square?
Maximum log n times.
Exactly, log n times. And this is the idea that we will use. Okay, and it works for matrices also. Works for matrices. Okay, so a to the n can be done by uh, by log n, order log n matrix multiplications. So this thing that I said that, oh, okay, every layer of circuit, so every time I do a cube, I add another layer of circuit. A4, I add another layer of circuit, and so on till an causes n log n depth of the circuit. This is true only if you do it trivially. If you apply this repeated powering, I won't do a cube, I won't do a4, a5, and so on. I won't do it that way. I'll just, if it is, let's say, for ease of purpose, let's say it is a to the 16, then first I'll calculate a square, then square that and square that, and square it. Okay, not 16. If it's 32, then I'll square it 5 times, 5 layers, okay, of matrix multiplication, and each layer is of log n depth. Then I'll get 5 log n depth of the entire circuit. So a to the n, oh sorry, okay, and so circuit can be made of depth. I want to compute a to the n means I am powering log n number of times, so order log n layers, and each layer we already know by converting from unbounded to bounded, like we did here. Okay, converting from unbounded to bounded, which increases the depth by log n. Okay, takes log n depth each of these layers, and total there are order log n layers. So that is order log square n depth circuit, which is of bounded fanning, which is also of polynomial size, and this means that this circuit is an NC2 circuit. So is that clear?
Yes, sir, clear.
Okay. Okay. Indumati, this I cannot go across this question again because it was a bit very long. But I suggest you to check the recording once, okay? And I'll move on. Okay, is that fine? Uh, the recording will be available. So this part, please check it online. I'll move on from here. Okay. Okay. So let's continue now. Yeah. Now that was that particular question. Okay. Now I just want to do a quick recap. Okay. And let's see where we can proceed from here. Um, so what were the things that we covered? We covered uh, unambiguity, not unambiguity exactly, but this promise problems, right? Promise problems, and this time we also covered in the lectures um, Wheeler-Vazirani theorem. And counting classes like sharp p, and finally Toda's theorem is not this time. Okay. This is it. Okay. So promise problems, Wheeler-Vazirani theorems, counting classes sharp p, and this fact that permanent is sharp p complete. Okay. And also that perfect matching, number of perfect matching is sharp p complete. Okay. So I'll now I don't have particular exercises that I can show you, but I'll do a bit of theory and a bit more in depth. Okay. Uh, so okay, I'll omit this. And okay, yeah, but I'll continue. Okay, so Wheeler-Vazirani theorem, what does it say? It says that if I have this something called unique sat or USAT, okay, is in P, then NP is equal to RP. Okay, unique sat is in P, then NP is equal to RP. And what does that mean? What is unique sat? Unique sat is phi is given such that okay, wait. Check if the formula phi is satisfiable. Check whether a formula phi is satisfiable where phi is has exactly one satisfying assignment if satisfiable. So well, um, first of all, so satisfiability. Okay, we know satisfiability is complete for NP. Question is unique sat complete for NP? That we cannot really say, right? Because we will need a proof for it first of all, and second thing is that can you can now I'll define something called UP. Okay, UP is characterized by non-deterministic Turing machines. Okay, such that okay if X belongs to the language, then there exists exactly one accepting path. This is UP, and U stands for unambiguous. Okay, U stands for unambiguous. Exactly one accepting path. So, what was NP? Well, there were several branching computation paths, and there could be more than one accepting path. As long as there is at least one, we are fine. But UP, unambiguous P, means that there exists exactly one accepting path. And this is not a syntactic model, this is a semantic model because this restriction is imposed on the Turing machine, right? And given a Turing machine, we cannot tell whether it is directly unambiguous or not. Okay, immediately it is not clear. And so, if it belongs to the language, there exists exactly one accepting path and it rejects. So, question is unique SAT contained in UP?
No, sir.
Why no?
Mm, there may be multiple accepting paths also. So
Okay,
then it may give wrong answer.
then it may be.
Sir,
Okay,
if
but okay. So but SAT is in NP, right?
yes,
So can you tell me why is SAT in NP? What is a simple NP algorithm for satisfiability?
NP algorithm.
Hmm.
So NP means like we kind of guess and verify.
Guess and verify. Let's say you do the same for unique SAT. Okay, let's say you guess and verify. But what is the special property of unique SAT? It's a promise problem.
Yes,
That
sir.
if I give you a formula that is satisfiable, I promise you that there is only one satisfying assignment that does it, solves it. So now let's say you to a phi to a given input phi which is satisfiable. Let's say I do the same guess. How many of my accepting paths will accept?
Mm,
It
it
is
can
it
be
is yeah
many also. It
yeah.
can be more than one also.
But why can it be more than one? I promise you that it is exactly. I mean, I promise you that number of satisfying assignment is exactly one if it is satisfied.
Huh. Then it can be only zero or one.
Yeah, then it can be only zero or one, right? So UP, the fact that unique stat is a promise problem that promises that there is a unique satisfying assignment for that formula. If I do the non-deterministic guess, then I'll have exactly one path that accepts and which I can term it as a UP algorithm, right? It won't be anything wrong to say because it satisfies the definition of UP. It is a non-deterministic Turing machine such that if X is in the language, there is exactly one accepting path.
Yes.
Yeah. Now, unique stat is in UP. Good, well and good. Next, um, now let me ask you the question. Unique stat, is it in NP?
Mm, I think uh, no.
Why not?
SAT SAT is in NP,
Stat is in NP.
but for unique uh, but for unique SAT to be in NP, we have to check for each and every possible inputs that it verifies or not. And if only one or once the satisfying assignment is there or zero, then it is only unique SAT.
Okay, okay. Now I get where the confusion is. Okay. Okay. So what, okay, this, okay. Unique stat, according to you, I think this is what you mean, no? Phi such that phi has exactly one satisfying assignment. This is what you're thinking, right, Suraj?
Yes, exactly one or zero.
But okay, exactly one or zero satisfying assignment. This is what you meant, no, Suraj?
Yes.
But
Yes.
this is not what Unix set is. Okay, this is some other language. This is some that we call it exact set. This is not a promise problem. It does not promise anything. It does not give a previous promise on what phi is. Okay, it just says you need to check whether there is exactly one or zero satisfying assignment. That is different from unique set. Okay, what unique set is phi such that phi is satisfiable. Okay, phi such that phi is satisfiable. Okay, and um, there is a promise which is totally outside all of this. So what you can even say is, so yeah, phi such that phi is satisfiable. Okay, and this is unique set, except the domain of phi is not a formula. It is not any other formula. Okay, phi is a formula. Okay, with exactly one satisfying assignment if it exists. Here what is phi? Any random formula. So this promise that is given is actually an external constraint. So this is the problem actually. So you cannot actually can you say that it is a language? So you cannot actually say that it is, that's why it's called a problem and not characterized as a language. Okay, the problem is as follows. The unique set can be written as the problem is one. Okay, unique set, the problem is outputs are one if phi is satisfiable and um, if phi is satisfiable and exactly one satisfying assignment. Zero if phi is not satisfiable, and don't care, meaning I don't care what the algorithm does if phi is uh, has greater than one satisfying assignment. This is the standard form in which it is given to us. But what I'm trying to say is, okay, here is a machine that I'm trying to create that solves unique set. Here's a machine that solves unique set. Here what I do is I as a user, you as a user, okay, give a promise that phi has unique satisfying assignment before inputting it to my unique set solver, and you don't lie. It cannot be that you promise me and then the promise is not fulfilled. Okay, so at the end I need to check satisfiability only, but the promise is that whatever you give me has a unique solution. Yeah, sorry, whatever you give me, that phi has a unique satisfying assignment. I already know that fact. Okay, so it is as if I'm already restricting the domain to a formula of a certain kind. This is only those set of formulas for which there is a unique satisfying assignment. So the problem is not to check whether it has a unique satisfying assignment or not, but the problem is to check whether it has a satisfying assignment or not, given the fact that I already know that it has a unique satisfying assignment if it exists. So do you understand the distinction here, Suraj?
Yes, I understood.
Okay, okay. So there is a promise already involved. Now, question is unique sat in NP? You already promised me. You already I already promised you that okay, this has a unique satisfying assignment if it exists. Okay, I already promised you. Then I give the phi to you, that formula to you, which has a unique satisfying assignment, maybe, and I ask you to give me an NP algorithm. Is it possible?
Yes.
Yeah. Okay. So how do you do it?
Uh, sir, so now it will be NP only, uh, because it is now the normal question of satisfiability.
Mm-hmm. Yeah, yeah. Go on.
Uh, Sir, what we have to do here? Uh, and,
Oh, okay. I'm saying, can you come up with an NP algorithm which solves unique sat?
NP algorithm.
Yeah, that
Uh,
is check satisfiability of the formula I give you, and I guarantee you that my formula, if it has a satisfying assignment, has only one satisfying assignment.
yes, sir. It can choose choose like string one by one, and it can change.
Yeah, that's correct. One by one, or do you mean guess it?
Means the
Yeah,
guessing only.
good. In fact, yeah. So the same algorithm for SAT works for unique SAT also, right?
Yes,
In the SAT also we are doing the same thing. In unique SAT also we are doing the same thing. And unique SAT, remember, it is complete for by Cook Levin again. I won't do this in detail, but unique SAT is an UP complete. Okay, so what does it mean? If unique SAT is in NP and unique SAT is UP complete, then UP is contained in NP. Right? UP is contained in NP. And what does it mean? Since unique SAT is okay, so also since unique SAT is in NP, it means unique and SAT is NP complete. We don't know about unique SAT. It probably means that um, unique SAT is weaker than SAT, right? Because unique SAT is here and SAT is here. Although the containment is not known to be strict, but we know unique SAT is here and SAT is here. So probably looks like unique SAT is weaker than SAT, right?
yes,
Right. Now this is what Valent-Vazirani theorem aims to do. Valent-Vazirani theorem aims to say that unique SAT is probably actually as hard as NP. Because if, let's say, unique SAT was solvable in polynomial time, then NP falls all the way down to RP, which is not expected. And RP is contained in BPP, and BPP is contained in P slash poly by Adelman's theorem. So that would mean NP would have polynomial size circuit, which is very unexpected to achieve. Then we are even more closer to go to P versus NP, P equals NP, which is very unlikely to happen. Okay, so therefore, expecting that unique SAT is in P uh, is likely not true. And so Unique SAT is probably closer to SAT, and unique SAT is probably as hard as SAT, in other words. Okay, that is what Vaillant-Vazirani theorem is all about. Is that clear?
Yes, sir, clear.
Yeah. So I'll just close off with one final thing on this unambiguity business. Okay. And that is, I want to ask about UL. We talk about UL, where U is again unambiguous. The question we are addressing is, can we talk about unambiguousness for log space? We saw unambiguous P, right? So unambiguous log space is non-deterministic log space Turing machine that accepts where X is in L if and only if um, Turing machine has exactly one accepting path. Okay, and so this is unambiguous log space. So we are just generalizing the idea to log space also. Now, question again is, both UL and NL are non-deterministic classes, right? So question is, what is the state of NL versus UL? Okay. So now there is a nice theorem. Okay. So now so we can ask the same question, right? How close is NL with respect to UL? Similarly, here we are asking how close is UL with respect to NL, UP with respect to NP, and we said probably they are very close. Probably NP is equal to UP. Similarly, question is, are they same or are they separate? So here's a nice theorem which is called the Reinhardt-Allender theorem, which was on 2000. Okay, Reinhardt-Allender theorem, which said that NL, and first you already see from same logic UL is contained in NL. Okay, from like same logic as before, is contained in UL/poly. In fact, they no, this is correct. NL is contained in UL/poly, and this is what they show in 2000. And probably NL and UL are very close, but of course it is upon an advice. If you remove the advice, then it won't work. But under an advice, they are same. NL is equal to UL. Okay. And question is, there have been several lines of research whether you can reduce this amount of advice that is given, and there have been better bounds here. And there is the direct question also: can you remove this entire advice at all? Now that no one has been able to do yet, but yeah. So talking about unambiguousness, there is unambiguousness in space also, defined in space also, and we have UL for that, and UL versus NL is the question for that, which is a big open problem in complexity theory, and this is the closest we've been so far. Okay, and also a quick interesting thing is that usually in theoretical computer science, and especially in complexity theory, if you notice the authors, the order in which you put the author's name is always alphabetical. Okay, because in a lot of experimental fields, computational fields, maybe something in physics, biology, whatever, and maybe AI, ML, and stuff. There is an idea about who contributed more. Right, someone did the experiments, maybe someone came up with the idea, someone did the surveys, and so on. But the idea in complexity and theoretical computer science is that you never know who comes up with the idea suddenly, right? Even when you collaborate, you may be having a bad day, you may not be coming up with an idea, and sometimes you may even be lucky and then come up with the good idea, and then it suddenly works. So the idea of contributions is a bit vague here. Is it really fair to actually say that okay, this person contributed, and sometimes of course you can say that this person contributed more, but usually to say that this person contributed more and so on, firstly it may bring in some kind of fights and arguments, and secondly it may not be fair in a very mathematical field where it is not clear that there's an element of luck and chance here. So the author's name are almost always alphabetical. Okay, for example, Cook Levin, C first and then L, and Valiant Waziran. Okay, Valiant Waziran is anyway this Karp-Lipton theorem, and Sipser. Oh, Sipser Lautenman is different now. I uh, see. Yeah, but anyway, it is in this order. But this is one of the few cases you've observed that the person with the the larger letter is ahead of the person with lesser letter, and probably it so happened that the authors believed that at least Allender probably believed that Reinhardt gave more of a contribution to the work, and but whatever the reason might be, this is a bit unheard of that we are switching to a non-alphabetical order. But yeah, I spoke a lot about that for no reason, but good to know. But with that, I'll end the session. So if you have any questions, just let me know. Okay. So do you have any questions, Suraj?
Uh, Sir,
Yeah.
uh, sir, especially in circuit theory means
Yeah.
I was facing difficulty in solving the question.
Okay.
Sir,
Okay.
is there any material is there which is easier?
Yeah. Yeah. Sure. Firstly, there are like several resources on YouTube. Okay. And but you don't. This course does not look. There is, I think. Okay. Okay. So firstly, YouTube is definitely there. There's a textbook. Okay. Um, Introduction to Circuit Complexity. Which is by Volmer. This is simpler than there is another by Stasis Yukna, which is Boolean function complexity. But definitely, this intro to circuit complexity is definitely simpler than Volmer, and the Yukna book is, it studies circuits mostly to study for the sake of studying circuits. Whereas Volmer book, it relates to the classical P and P stuff and gives motivation. So, and it is in a simpler fashion. It is written in a simpler fashion also, and and there is, of course, YouTube is there, and I think there is CMI, not CMI. TIFR should be having a course on this. Okay, or you can check courses by Simon's Institute. I'm not sure whether MIT has a course available on YouTube or not. And on NPTEL, there is a dedicated course for circuit complexity. Okay, and this is by Raghunath Tiwari, and he's a professor at IIT Kanpur. He has done a wonderful course on circuit theory, yes, circuit complexity theory in NPTEL. So you can check these out. Additionally, you can just search for written lectures, okay, of on circuit complexity, and there'll be several, late well written lectures, okay, which you can read. Okay, if you don't want to go in depth as a textbook fashion, you can read those lectures from uh, good courses from good institutes, and you can just Google it and then you'll find it. And of course, if on doing that you are facing some kind of problems, then of course in the next problem session you can point it out to me what problems you are facing, okay, and then we can discuss about it. You can also email me. I'll write my email here once again. So here's my email, okay, so you can message me here, and we can probably discuss, okay, and I'll, if it's a problem, then I'll work it out and then come back to you. So is that fine, Suraj?
Mm, yes, sir.
So by the way, so your what is your, yeah, I'll just end the recording.